Hi everyone, this is Miss B. So we're going to continue along with our unit on gases. So for the rest of this unit now, you'll be learning the gas laws that explain properties of gases. So if you remember, there's four variables or four letters that are involved. There's P for pressure, V for volume, T for temperature, and mole. Mole is actually going to use the letter N as in no, but you don't need to worry about that now. That'll come along a little bit later, but I think the letter M was already taken for mass, and that's why the letter N is going to be used. So as I introduce these gas laws, we're going to start with just a couple letters at a time, because this is how an understanding of gases progressed, right? Scientists looked at different variables to see if they could figure out some just general ideas about the gases around us and the atmosphere and so forth, okay? So we're going to start with just a couple letters at a time, and then we'll start to combine them. Now, as you solve these gas laws, keep a calculator handy. I go through one example of each, and in terms of setting it up and solving it, I'm pretty detailed on how to do that. Not all of you will need that much detail, but it is there for everyone's reference. Okay? And one last thing you'll see it up on the screen. Usually the gas laws are solved in liters for volume. That's the capital letter L, so careful if you see milliliters, you have to change that to liter. And then Kelvin for temperature. So I did ask you to practice how to convert Celsius to Kelvin. It is not too difficult. You have to add 273. You just have to remember to do so if a law requires temperature. So the first law we start with is Boyle's law. And I think you know that I like the scientist, so there he is. That's Mr. Boyle. You don't have to know all of this background, but I think it's good for you to know how these concepts were determined. What were people looking at, and how did they figure things out? So he's an Irish scientist, and he performed experiments that looked at the relationship between the pressure of a gas that is trapped and its volume. So these would be the letters P and V. The temperature at which he did this and the amount of gas that he used were constant. So T and moles will not be involved in this law. Now I have a couple websites to help you understand this. We have the NASA website, which I will show you second. I'd like to show you this one first. All right, so what you're looking at here, let me get to it. This is called a manometer. It's a J-shaped tube. This was more of a J-shaped tube. I think they don't have to be a J. They could be just like a big U tube at this point. And what he did is he put some mercury in there. So that blue color that you see is liquid mercury. Now the top of the J tube was opened to atmospheric pressure, and the closed part, the tip of the J, you'll see there's a little bit of space in here. So that's trapped air inside this tube. So what he did is he would add mercury, which increases the pressure of that air inside that J tube. So as he added mercury, something would happen to the volume. So the more mercury that he added, that was creating more pressure. So as the pressure was increased, this space was decreasing. So it's an inverse or opposite relationship that he was noticing. Okay, this is his original data, so you can just see all the ways that he messed with the pressure and then watch the volume. But what also happened was, okay, so he's got like pressure here and volume here. So as he increases it and then notice that the volume decreases, well, what happens if you just apply some mathematics to this? So what he did is he actually multiplied pressure and volume all throughout his data table. And what he noticed is that as he multiplied these, the answer remained pretty much the same, or a constant. Okay, now let me back up to, this is the NASA website. So it's kind of the same concept, you just don't have the J tube. So I thought this would be a little bit more visual for you. So we have two different situations, the left side versus the right side, and just watch all the variables, right? Mass, that's the mole, right? Stays the same, does not change. Temperature does not change. So T and mole is not involved. Now pressure is going to be altered, and then this blue little section right here is going to measure volume. So what's going to happen if we mess with the volume or mess with the pressure? What's going to happen to the gas? So here it is. Okay, so if you notice now, as the pressure goes up, right, it's going from 1 to 2. What's going on here? The volume is going down. So pressure goes up and volume goes down. So this is actually what Boyle's law originally looked like if you were to graph his original data. So this graph where it's curving downward is called an inverse relationship. So they're opposites, right? What you do to one is not going to happen to the other. The other is going to have the opposite effect. So this is what Boyle was originally looking at. Okay. So this is that same data table that I showed you. I just pulled some of the data here. So here he is manipulating the pressure and then watching what happens to the volume. So for each instance that this occurred, if you multiply pressure times volume, look what happens here. The result, that's not identical, but it's pretty close to that 1400 range. So he was noticing something, right? Something was going on here with his experiments about air pressure and then its effect on volume. Okay, so again, just to explain this one last time, as the pressure increases, right? So he would add more and more mercury into that tube, that increases the pressure. The volume of that little space decreased, okay? So, or you could reverse it, right? If you decrease the pressure, if you remove some of that mercury, the volume would go back up, okay? Now he used mercury, but you could use, other things. That just mercury was used at that time because it really shows a rise and a fall pretty well. All right. Now, in terms of the law itself, right, he took pressure times volume. He applied some math to this just to see what was going on just mathematically. So he took pressure times volume and noticed that for the most part, if you don't involve temperature, don't involve the amount, P times V is going to stay the same. Now that's not what we really need to know. I don't really care that you know that that's a constant. I'm just showing you the background here. So here again, I just took two of his results and tried to show this to you. This is not what I need you to be able to figure out. My point is, I'd like you to watch some changes based on his law. So you could just do this all the way down his data table, like P1 times V1, that's the first experiment. P2 times V2, and so on. 3, 4, 5, 6 down the line. So if these are staying constant, then each experiment could be equal to each other. So Boyle's law is referred to as this. P1 V1 equals P2 V2. So what I would like to know, just in general, right? So let's say you just had like a helium balloon, right? There's so much pressure and there's so much volume, right? So if you release that balloon up into the atmosphere and it rises, right? That pressure is going to decrease. What would happen to the volume of the balloon? And if you know anything about helium balloons that are released either accidentally or on purpose, as they rise up, that pressure will get smaller and the balloon would actually pop because the volume would be increasing and it couldn't hold the gas any longer. So that's the kind of thing that I'm looking for you to figure out, like different situations. So if I give you 3 of the 4 letters, can you get the 4th letter? So that's the point. Okay. All right, so let's try the example that I was just describing here. So what happens to the volume of a helium balloon if it's let go? And here's my values for you. It's got a volume of 20.0 liters and a pressure of 1.0 atm. So that's my original P and V. It ascends, right, or is released and moves to a height that drops the pressure to 0.1 atm. So pressure dropped, volume, what's going to happen? So in your mind, just by common sense, understanding the law, you can probably guess what's supposed to happen. But with chemistry, we can always prove things mathematically. So here is how we solve this. Okay, so it's P1 V1 equals P2 V2. Again, you do not need to memorize these laws. You need to know how to use them. So there's a lot of laws in this unit. You are not expected to memorize them. I just hope that you understand what they mean and how to solve them. Okay, so let's put in our values now, right? So the balloon had a volume of 20 liters, that's the first volume, and a pressure of 1 atm. So that's like the balloon in your hand. So much pressure, so much volume. So this 1.0 is sea level, right? That's your standard ATM. So if we release it, it's going to rise to a height that we don't need to know the height. We just need to know what's the pressure at that height. So the pressure drops significantly to 0.1 atm. What happens to the volume of that balloon? So I know some of you at this point Could just plug this in and solve for V2, but if you need a little help as to how to do so, let me show you the algebra. All right, so what I did is I took 20 liters, I took 20 liters and I times it by 1. So 20 times 1 is just 20. Now I left the ATM and the L here because you have to know how to solve with proper units. So they haven't canceled, nothing's canceled out, so they're still there on the left-hand side. Now it's equal to still 0.1 ATM and V2, nothing was canceled here. Now the goal is you are trying to get V2 by itself. So if these two are next to each other, that means they're multiplied, right? So to get rid of 0.1 ATM, to have V2 by itself, you will need to divide. So now V2 is alone, and we've got all that we need on the left-hand side. So it's 20 ATM times liter divided by 0.1 ATM. Now, if you notice, we have two similar, so if you have two units that are the same, they can cancel. And this should make sense because we're trying to solve for volume, which would be in liters. So to solve this, it'd be 20 divided by 0.1, and your answer is 200 liters, which is V2. And we're just going to avoid significant figures for now, just solve the problem as is. If we have decimal places, we'll just keep them to 2 for right now, okay? All right, so here's your answer. It's 200 liters. Now I just want you to think, does this make sense? So the balloon was at 1 ATM, so that's standard pressure, and 20 liters. You let the balloon go, it rose, which drops the pressure to 0.1, so pressure went down, so our volume should go up, and it did. It went to 200 liters. So this is Boyle's law, and I'll have a couple of these for you to practice as soon as we could get through the first 3 gas laws.